Hello everyone, this will be the last video for dealing with Appendix A, and in this one we'll be talking about inference, confidence interval estimation, as well as hypothesis testing. Alright, statistical inference, all we mean is making guesses about the values of population parameters based on estimates computed from sample data. So examples of the types of questions we want to ask when doing inference are the following. If a sample mean is equal to some value, what is the likely value of the population mean? Also, we might want to compare the values of two variances of two distinct random variables. Okay, now when we do estimation of population parameters, or when we estimate statistics, we can develop point estimates as well as interval estimates. Point estimate is merely a single value estimate. So the estimator for the mean, for example, produces a point estimate. But we can go on to develop interval estimates, which gives us a range of possible values for mu, say. And we call these confidence intervals. Okay, so what are confidence intervals? They give us a likely range of values for a given population parameter. They have a lower limit and an upper limit, and it's usually the value of these limits is determined by, among other things, crucially, the significance level alpha. In the case of mean, we will use the t-distribution to determine confidence limits, and we will look this value up in the t-table. To do so, we will need the degrees of freedom given by n-1, as well as a given alpha value. The alpha value we will usually select will be one of these three numbers. There's no magic here. There's no scientific reason for this. This is just purely determined by convention. And what we are saying ultimately here is that, for instance, if we select an alpha value of 0.05, we are saying that if we repeatedly sample data from a given population and estimate means, there will be a 1 in 20 chance that the true population mean does not lie within those estimates. Well, that isn't entirely accurate. What it tells us is that in repeated sampling, if we sample from a given population over and over, and we estimate confidence intervals in each case for the mean, say, in 5% of those estimates, the true population parameter will not be represented. And that is why it's usually ideal to have a smaller alpha value. The disadvantage of having a smaller alpha value is that you have wider confidence intervals, and at some point they are so wide that they are essentially meaningless. Okay, so this next couple of slides will introduce you to the method for estimating confidence intervals for mu based on the sample statistic x bar. So the equation at the top is read as follows. The probability that a statistic which follows the t-distribution lies between two t-values from the t-distribution table is equal to 1 minus alpha, or is equal to 95%. So what we want is to isolate mu between these two inequalities. And with some algebraic manipulation we can do that, and we end up with the second formula on the slide over here. Now, we can estimate confidence intervals if we have a sample of data, as long as we can compute the mean, the standard deviation, and as long as we know the sample size. Then all we have to do is look up the t-values in the t-distribution table. So let's look at an example. Here we're given a sample mean of 20, standard deviation of 3, and sample size of 25. These three values we can just plug into the formula on both sides of mu. And then what's left is to look up the t-value in the t-distribution table. Just note that the small s over here should be a capital S. So looking up the t-value, here we have the t-distribution table. We note that our sample size is 25, so degrees of freedom is 24. Hence, we're looking for a number in this row. And the alpha value for the first question was 0.1. Hence, we're looking for a value in this column. So the number that coincides with that row and that column is 1.711. And you will notice that the number 0.1 appears in 2 columns in this table. And if you're unsure of where to find which column to use, just read the note at the bottom of the table, which would give you an indication. So it says here, the smaller probability shown in the head of each column is the area in one tail. The larger probability is the area in 2 tails. And when we're estimating confidence intervals, we always want the value for 2 tails. Hence, we want to use the column where the significance level is the larger value. And in this case, it is column 4 of this table. Okay, so just going through the solution, here we have a confidence interval for mu of between 18.9734 and 21.0266. So how do we interpret these numbers? Well, remember that confidence intervals are estimated using sample data. And if we should draw another sample of the same size of 25, we would in all likelihood get different values on either side of mu over here. And in fact, the way to interpret this is as follows. We say that in this case, in repeated sampling, in many samples drawn, many confidence intervals estimated, mu would be represented in 90% of such confidence intervals. That's all we can say. We don't know whether these 2 values are necessarily one of the 90% or whether it's one of the 10%. We have no way of knowing that unless we repeatedly sample over and over and over. We can get a better sense of what the true population parameter is likely to be. However, in most instances, we don't resample over and over and over. We draw one sample from a population and we estimate a confidence interval. So it's important that we're very careful in how we interpret that. Okay, so that was confidence interval estimation for mu. We're also interested in estimating confidence intervals for sigma squared based on the sample estimate of standard deviation of the variance S squared. So we follow the same process. Here we have a different statistic, of course. This statistic follows the chi-square distribution. So you'll see chi-square values on either side of the inequalities. And one important difference between confidence interval estimation of sigma square versus mu is that given that we're using a chi-square distribution, we have to look up the value for each side of the confidence interval separately. In the case of the t-distribution, we only look up one value because we know that the t-distribution is symmetric. So the value in the left side will be the same as the value in the right side. You just put a minus sign on the left side because, of course, the mean of the t-distribution is 0. In the case of chi-squared, we know that all chi-squared values are positive because it's derived from a squared random variable. And we know that the chi-square distribution is usually asymmetric. Therefore, the value in the left tail will not be the same as the value in the right tail. Okay, so in this case, we want to isolate sigma squared between the 2 inequalities. And once we do that, we end up with the second formula on this slide. So let's apply an example. So here we're given a variance of 12 and a sample size of 25 once again. So we plug the 12 in over there, we plug 25 in over there. Now what's left is to look up the chi-square values in the chi-square distribution table. So here we have the chi-square distribution probability table. And again, what we need is our degrees of freedom as well as our significance level. So for the first question of significance level 0.1, we have degrees of freedom 24, again n minus 1. So we're looking for a number in this row over here. Now we need to determine which column we're going to choose our value from. And here I want to go back to the formula once again, because here the formula matters a bit more so than it does with the t-distribution. So notice on the left side of the inequality, you have chi square alpha over 2 for k degrees of freedom. On the right side, you have chi square 1 minus alpha over 2 k degrees of freedom. Now, alpha value for the first question is 0.1. So alpha over 2 will be 0.05. So to get the value on the left side, we have to look for a column, the column in the chi-square distribution table, which has 0.05 at the top. In other words, we're interested in this column over here, and it so happens that the degrees of freedom are given by this row. It's not indicated on this particular page, but this is what it is. And so the number that goes into the left side of the confidence limit formula for chi-square distribution is 36.414. Then for the right side, we need 1 minus alpha over 2, and 1 minus alpha over 2 being 0.05, 1 minus alpha over 2 would be given by 0.95. So this is the column we're interested in over here. 24 degrees of freedom, and the column header of 0.95 coincide with this value, 13.8484. So remember, this goes into the right side of the confidence limit. So plugging those values in, we obtain these estimates. So the variance lies somewhere, well, the confidence interval is given by 7.9088 and 20.7967. Again, the way we interpret this is that should we sample data over and over, calculate sample variances, and estimate confidence intervals based on that estimate. In 90% of cases, the intervals will include the true value of the standard deviation. If we have drawn one sample, we don't know whether our particular confidence interval is one of the 90% or one of the 10% that does not include the true variance for this given population. Okay, let's look at some properties of estimators. And we'll revisit these again when doing regression, so I won't spend too much time on this. An estimator is simply a linear estimator. If it is a linear estimator,